In this lecture, we will be looking at the concept of leverage in multiple linear regression. So let's think about regression. Recall this is our regression model where we have the ith response is this linear combination of the p predictor variables plus an intercept and a white noise term. And we have n total observations of the predictor vector and the response variable. We saw in our normal equations lecture that the overall regression as a least squares problem can be written in this following way, as long as our x vector has full column rank, where this matrix here, this x times quantity x transpose x inverse times x transpose was called H, or the hat matrix. And if you look at this matrix, recall that X was a tall, skinny matrix. So X was n by p plus 1. So n rows in p plus 1 columns. So one row for each observation, one column for each of these betas. That means that this H is an n by n matrix. And since it's an n by n matrix, it has a row and a column for each of the n observations in our data. We then define the leverage of the ith observation as the ith diagonal element of that hat matrix H. And the idea here is that the leverage for the ith term, HII, is large when the predictor variables for the ith case are atypical compared to the rest of the data. In other words, when the observation for the predictor is an outlier. If you think about this in the case of a univariate regression, if you have a bunch of points like this, say kind of clustered together, and then you look at all the x values for these, all the predictor values, we see that they're clustered together here. But if you had one value for the predictor that was far out here, this would be a point with a high leverage value. Now note, we're not specifying anything about the actual response value. You could have something here, or you could have something here. And note that this is pretty consistent with the regression line that would be formed by these points on their own, whereas this one is not. And it's important to note that this high leverage is associated just with the observation of the predictor being atypical from the rest of the data. We will look at this issue of the response being typical or atypical for a high leverage point later in the next lecture. But for now, this is what that large leverage factor for the ith case would be picking up. Now, one key property for these leverage values is that they all are in the open interval 0, 1. And then if you take the average of them, you get p plus 1 over n. So this is p plus 1. Recall that is the number of beta coefficients in the regression model, and n is the number of observations. A general heuristic rule is that if any single leverage value is bigger than 2 times p plus 1 over n, notice what this is. This is just saying double the average. So if you see a leverage that is more than twice the average, then we consider that large and a possible cause for concern. That doesn't mean that you have a bad data point. It means it's something that you should look at. And then we would decide whether or not it's what we call a residual outlier, which is something we will show in just a moment. First, let's look at a special case just to get some intuition. In the univariate case, where p equals 1, so ordinary single variable linear regression, where we have an intercept beta naught and a slope beta 1, plus our noise term, we have a nice formula for the leverage, HII, and it's 1 over n, plus this fraction. And we can make some sense of this by noting if you multiply top and bottom of that fraction by 1 over n minus 1, what we have in the bottom is the sample variance of the predictor, x, and in the top we have the contribution. See, there's no sum here, so this is just the one term for the ith case. And so this numerator is the contribution of the ith case in terms of the one term it contributes to the sample variance. So we see here, this is how much, the squared difference of how much the ith observation for the predictor deviates from its sample mean. And so if it is atypical, then this numerator will be larger than the cases for the other observations. And that's what gives you a large leverage value. So you can see in this case, in this univariate case, how this xi being atypical gives you a bigger term here than its typical counterparts. And that leads us to the geometry of this. So let's think about this case, univariate regression, where we have a cluster of points, and then let's throw in a point with a large leverage value. So the idea is that these are similar or the same cluster. And if you were to do your regression line, in this case, and suppose actually that we have this high leverage point over here, and so recall that if it has high leverage, our predictor is atypical, so further off to the right. But in this case, this is going to be what we call a non-residual outlier. And we'll explain what we mean by that in a moment, but let's put our data point, say, up here. And now, if we do our regression, we should get a regression line that looks something like this. It's our least squares fit, best fitting line that go through this scatter plot. And we call this a non-residual outlier because this point looks like it's consistent with this linear model. Now suppose over here we have a point with the same leverage value, but the difference now is the data point appears down here. And if we think about what will happen with our regression line, the regression line takes the squared errors, adds them and minimizes them. So the vertical distance between each observation and the corresponding point on the line. The issue is here, this is going to, imagine taking this point and moving it down here. There will be a very large error term associated with this observation. And what will happen, and this is one of the reasons why we call it leverage, is moving this point down here will cause us to pull down on that regression line like a lever. And the resulting regression line will look like this. And the issue here, in this case you would have a residual outlier, is the residual associated with this data point is large. So if this is our ith data point, this is going to be our epsilon I hat. Over here, our epsilon I hat is small. And you see, not only is this large, but it completely messes up our regression model. We can see that this line really does fit much more appropriately most of the data than this line. And this high leverage point and it being a residual outlier is what did this. And so this is really what makes this concept of leverage a handy tool. Because anytime you're doing a regression, you have to be careful with your data. So we've looked at an entire set of tools that we can use to critique a regression. But now we want to critique our data while we're doing our regression. And so this idea of using leverage to try and identify these types of residual outliers is extremely useful. Number one, because anytime you're doing regression, outliers can cause this kind of dramatic effect on your model, and that's either appropriate or it's not. Sometimes this is a real outlier. Sometimes it's just a mistake in your data set. And if it's a mistake in your data set, you want to pick up on this. And one might say, well, maybe we could pick up on this visually. Yes, this may be true in this type of case where we're doing a univariate regression. But what if you're doing a multivariate regression in higher dimensional space where you can't plot the graph? You want to be able to have these types of tools so that you can look through your data set and detect, or maybe a better way to say it would be to filter your data set and detect these types of anomalies that may have a pretty dramatic effect on the model and may or may not make mistakes in the data. One thing you can do with this concept of leverage, we have a leverage value for each observation in the data set. So one natural approach is to compute all of them and look at them on a histogram. Look at the large values. And that can help you get an understanding of what's actually happening, not only with your data set and maybe pick up on mistakes, but also what's happening in terms of outliers and the type of effect that they have on your model. Now we will follow this up with a lecture on the idea of detecting the residual outlier. Can we actually see the difference in terms of ways to understand the error, the epsilon I hat, to pick up on the idea that we have a high leverage residual outlier versus a high leverage non-residual outlier. And so that will be the next lecture.